welcome to the second half of this lecture, in which we move on from data structures to talking about a randomized algorithm. In particular, we are going to look at a randomized algorithm for the mincut problem, and this was proposed by David Karger. And for this very fundamental problem, and let me motivate this problem first. And here in this slide, we have three graphs, and if these were network graphs and you were concerned about the robustness of the network, how easy it is to disconnect and things like that, quite obviously you will notice that this graph is very bad. This graph is okay, and this graph is good. And what makes you spot this? Because you can see in this graph that a single edge, if it is deleted, can disconnect the entire the graph into two components. And so this is the nature of real world issues that motivate the mincut problem. And chances are you have seen this problem in the context of a flow based solution, but in today's lecture we are going to talk about a very simple, elegant randomized algorithm for this problem. And so let me define the problem. We have as input a graph G. It's an undirected graph and it's an unweighted graph. A cut is simply a partition of the vertex set into two sets. So if you this is your set of vertices, a partition into set S and V minus S is a cut, and the cut set corresponding to this cut will be the set of edges with one end in S and the other end in across the cut in V minus S. So, all these edges that go across the cut comprise the cut set. Now, our goal is to find the partition, the cut, such that the corresponding cut set has least cardinality. And so, naturally, this is called the minimum cut or the mincut problem. So, as I mentioned earlier, you may have seen a flow based algorithm, but in today's lecture we are talking about a randomized algorithm, and here is how the algorithm goes. We start with the full graph, and we repeat this next two steps until finally we are left with just two vertices. So, in each iteration we pick an edge u v uniformly at random from all the edges that are currently in the graph. And once we pick an edge, we contract that edge. And what do we mean by that? We coalesce the two vertices. So, the edge u v is connecting vertex u and vertex v. We coalesce them into a single vertex. And so any edge between u and v now becomes a self loop. So, we simply remove those self loops, but then there could be multi edges, and we will see how such multi edges could form from an example that we will look at shortly. So, we will be retaining the multi edges though. The self loops we will discard, but the multi edges we retain. And as we coalesce, we keep track of the super nodes and the real original nodes that were actually that they actually comprise. So, each super node was formed by smaller super nodes or smaller original nodes. So, we keep track of all of that, and finally, we will be left with two vertices after n minus 2 contractions. And so, we will be left with two super nodes, if you will, with possibly several multi edges going across from them. But each of these super nodes actually is made up of several original nodes. So, let us pick one of these super nodes, and the set of nodes that they actually are contained in this super node is simply S. So, which means that this would be V minus S, and this is our candidate cut. The claim now is that with a good probability, non-zero probability, in fact, 1 by polynomial in n probability, S and V minus S actually induce the smallest cut set. So, this seems quite magical. Let us look at an example that might give us some intuition as to why this is true, and in the subsequent segment we will actually analyze it more carefully. So, let us look at how the algorithm operates, and this is our original graph, and as you can probably see by just eyeballing it, this is going to be the minimum cut, and this execution that we are going to see now illustrated here actually is going to discover that particular cut, min cut. So, let us see how that works. So, there are several edges. The algorithm picks one of these edges uniformly at random. So, let us so here the edge that is picked is this one, and so it is connecting two vertices u and v. We call it u and v. So, now this edge has to be contracted, and we get a super node that, and this super node includes both u and v. And of course, the self loop is thrown away, but notice that there are multi edges that are created. So, for example, there is an edge between v and let us say call this x. There is also an edge between u and x. Now, between the super node that includes u and v, we have to include both of those edges. Okay. And then we proceed, and similarly all other multi edges also notice are being retained. So, we now again randomly choose one of the edges, and notice that these multi edges you cannot discard them. So, each one of the multi edges is also a candidate for being picked. In this case, let us say this edge is picked. So, we contract those two vertices, we get this super node, and notice that we get 4 multi edges over here and 2 multi edges over here. We retain all of them, and we proceed with this in this manner. So, again we pick this edge uniformly at random, contract it, we get this new structure, and look here, one of the multi edges here is being picked. Again, contraction takes place, self loops are thrown away, and this procedure is continued. Notice that we are retaining all the multi edges. We continue on, and finally we will be left with a scenario like this, where you have 2 vertices and a few edges going across them, and each of these super vertices, if you will, or super nodes, is actually representing a larger set of vertices in the original graph. So, let us if we have to keep track of them. So, let us say this super node comprises the set S, and this super node comprises the set V minus S. Our claim, of course, is that this cut, the cut induced by S and V minus S will in fact be the minimum cut with probability at least 1 over n choose 2. And that is the proof of this claim will be, we will study that in the subsequent segment.